Good afternoon, welcome, and thank you for joining us for our second webinar in our series, Enabling Effective Coatings Formulations to Improve the Durability of Assets, presented by Huntsman Advanced Materials. If you are looking to reduce costs, downtime, and your carbon footprint whilst prolonging the lifetime of metal structures, you are at the right session with us today. In a few minutes, we will introduce you to component solutions which enable sustainable formulations for highly corrosion-resistant protective coatings on metal substrates. I am Sarah Fernandez, European Operational Marketing Manager for the Coatings and Construction Industries, and I will be your moderator today. Let me start outlining the main differences between the content of our previous durability session in May and today's one. At our first durability webinar, we provided insights on polymer design and kinetic features to support formulations of highly chemical and temperature-resistant coatings. Today, we will guide you through polymer design attributes with special focus on fast cure, addition, and carbon footprint for the development of highly sustainable and corrosion-resistant coatings formulations. At this point, let me remind you a few house rules. This webinar will last approximately 1 hour, with enough time for questions at the end. You may submit your questions at any time by using the WebEx Q&A tab on your screen. Please be in mind to address your questions to all of the panelists so that we can make sure we don't miss any question. Those questions not addressed during the live event will be answered offline in the next few days. After the webinar, we will share with you the PDF file of the presentation by email. Please note that this webinar is being recorded and will be made available soon at the Huntsman website under the News/Webinar section. Should you be immediately interested in a follow-up discussion, please contact us via WebEx chat during the webinar. Alternatively, you can submit your inquiries at the Huntsman website via the Contact/Advanced Materials section, or you can contact your local sales representatives. Finally, we would much appreciate your participation to our survey at the end. Your feedback is key to help us improve our next webinar sessions. At this time, I would like to introduce today's speakers. Dr. Alex Dureau is our European Technology Manager for Advanced Materials, taking care of the specialty components portfolio in the aerospace, coating and construction adhesives, and composite applications. Mr. Dureau has more than 15 years of expertise in the chemical industry. Mrs. Kerstin Schreinemeyer works as Global Strategic Marketing Director for the coatings, construction, and electronics industry for Advanced Materials, and she has held multiple high-level responsibility roles related to the coatings applications for almost 30 years. What are the topics that we will be touching today? Firstly, we will be opening with a brief introduction to our sustainability drivers and commitments, followed by a high-level overview of science fundamentals on addition, hydrophobicity, and flexibility as key parameters leading to high corrosion resistance performance. We will continue showcasing polymer design features of epoxy systems, as well as requirements and implications of using high solid components in your formulations. Afterwards, we will deepen into our component solutions for coating formulations on compromised substrates, as well as solutions that address faster and lower temperature curing needs while meeting your most demanding sustainability requirements. At the end, we will conclude with a high-level summary of key formulation attributes and our final selection of component solutions to enhance those. So, Kerstin, could you please tell us more about Huntsman making use of a mass-balance approach for bio-based feedstocks and, of course, our key drivers in Huntsman's sustainability strategy?
Yes, sure. Thanks a lot, Sarah, for your nice introduction. People safety and product safety. It is and has been for a long time of high importance in all our developments. And consequently, we are the leader in SVHC-free Hardener technology and are often the lead registrant for new materials. This is also very visible when you look at the amount of bio-based material in our products. Alex, could you maybe go to the next slide? Thanks a lot. So we have been a very early adopter of the mass balance approach, and this will be officialized with a certification process during 2022. What you see on this slide is basically also the description what the mass balance principle actually is all about. It is actually the certification of a mix fossil and renewable raw materials and a way of keeping track of those bio-based components with regard to their quantity in individual products. On this slide, you can actually see some examples of our resins and their renewable content in their formulation. You will see more examples in the following slide, which you have here. And this is basically examples for some of our hardeners out of our Hardener product family. So with that, let's move over to discuss some fundamentals for corrosion resistance and the polymer structure. So by the way, Alex, thank you very much for coloring those structures. I really like that.
Okay. Good afternoon, good morning, everybody. So let's start with the key parameter for corrosion resistance and what they are. On the left side, we schematize a coating onto a substrate, and you can see there is potentially direct attack of water onto the coating surface. And you understand that the hydrophobicity of the coating material should be good enough to limit the permeation of water and potential blister, basically. The other main parameter is the ability to maintain an excellent adhesion between the substrate and the coating in case of crack, which will lead to a side attack and potentially break the adhesion link. So the adhesion is also really key for anti-corrosion as well as flexibility of the coating to avoid crack. On the right side, the concept of adhesion is described. It is a combination of adsorption, chemisorption, and sometimes diffusion. We could also say affinity of the coating material with the substrate, which are van der Waals bond, or covalent bond between substrate and polymer. Other influencing parameters for adhesion are the wettability, the type of substrate, compromised or not, and the potential shrinkage of the thermoset upon cure. Here we speak about the polymer network design and the impact on performance of the formulations. As mentioned before, the coating matrix is important to ensure good adhesion and hydrophobicity. On the left, we have plotted different resin and hardener in a matrix. In x-axis, the aromaticity, and in the y-axis, the functionality. In general, a very functional component will lead to higher cross-linking density, hence lower flexibility and lower adhesion. The lower aromaticity leads to lower hydrophobicity and lower viscosity. All of that to illustrate that you need to be careful when you choose the component to formulate a good anti-corrosion coating. You can see that the typical hardener polyamidoamine was placed in a good compromise of flexibility and hydrophobicity. It is the orange molecules. And we can say also that would be the case for most of the hardener. On the right side, we are showing the mix ratio influence between resin and hardener. In the middle of this table, the ideal mix ratio between two components, let's call it stoichiometry, and generally it is 2:1. When you add more hardener, it means you're going into the 1:1 direction, and basically towards the right side of the table, you generally increase reactivity. So you have an effect on pot life and dust free time, and you also flexibilize the system. The effect on the adhesion is then good, but the hydrophobicity is reduced. Overall, in this case, the corrosion is worse, in fact, but you increase the reactivity. Now, all parameters are inverse when you put more resin than you should, meaning going towards the left side this time. And what we can say with this stoichiometry, this mix ratio, is that generally epoxy chemistry is pretty versatile, and you can really play with this mix ratio to adjust your need. Surely not going to the extreme 3-to-1 or 1-to-1, but slightly going away from the 2-to-1 is really possible. Now let's speak about the implication of the technology choice on performance and drying. And the different technology we look at here are the solvent-borne, or the solution, the waterborne, so water, and the 100% solid. So historically, the favored one was the solvent-borne, but because of the solvent reduction trend, there is more and more waterborne as well as isolate to 100% solid. On the left side, you can see an attempt or scheme of the three systems, from the pot to the coating before cure and to the dry film. Clearly, solution and waterborne with evaporation of solvent or water will lead to a thinner film compared to the 100% solid system. Generally, in solution and waterborne, there is a possibility to get a large level of physical drying and a longer pot life, which is clearly not possible with an 100% solid, as you need to use much lower viscosity material and higher reactivity components. You can see that, or you could see that on the picture if you see it, with the high density of reactive group in case of the 100% solid. The challenge of 100% solid is to get a chemical conversion in a decent time. The consequence of 100% solid is also the much higher cross-linking density, so there is a need to be smart to achieve a certain degree of flexibility. The challenge of waterborne is more the need to have a low humidity environment and not a too low temperature, as water do not evaporate so well otherwise. Also, we'll see later, the challenge of waterborne is a non-visible end of pot life. And on the right side, we summarize the pro and con of the three typical systems. And if solution seems to be the best compromise, it requires a large amount of solvent. And now it's a matter of optimization for high solid system to take advantage of small usage of solvent compared to the 100% solid. So on this table, we summarize all the products which are going to be mentioned in the presentation. They are all related to sustainable solution, as it is the theme of the webinar. They can be sustainable for different reasons, and the better EH&S profile is something common to all, either in the efficiency part or in the durability part. EHS part can be about VOC reduction, SVHC free, meaning substance of very high concern free, or biorenewable contents. We chose in this presentation to mention exclusively SVHC free material. And now in the efficiency part, you can see that it's about adhesion and uncompromised substrate, or the ability to cure low temperature, at low temperature, increasing working season, especially in area with cold winter. Durability is about performance in anti-corrosion, impact resistance, and adhesion, allowing a longer lifetime of the asset. We have clustered the product chain by family: epoxy resin, curative, reactive diluent, and waterborne product. The booster are additive like accelerator or adhesion promoters that you can use in small amounts. So let's start with the sustainability solution efficiency, related to efficiency. So here we have clustered or put together the curative families, and we did cluster them in three groups. And on the left side, you can find the Hardener for outstanding chemical resistance, thermomechanical resistance, that we discussed last webinar. In the middle, the multi-purpose Hardener, which can be used or co-used for many applications, either to speed up a reaction or to be a good compromise between chemical resistance and adhesion. And on the right side, you will find the polyamidoamine-based component, which provide a superior adhesion than the other family. Typically, they are the perfect choice for anti-corrosion coating. Let's focus now on multi-purpose Hardener. And why those one? Because they are SVHC free, high solid content, or easy to apply. As mentioned before, there is always a need to limit the VOC content in our hardener. For instance, benzyl alcohol is a VOC now. And with the REACH legislation, there was more and more product which became SVHC. So SVHC, or at least we did contain SVHC, so bisphenol A, phenol, nonylphenol, and so on and so on. Recently, there was even the surprise with the salicylic acid, which also became SVHC. In that view, we proactively often try to replace those concerning chemicals, and you see sometimes in our denomination something -1. -1 is because we remove BCA and replace by something else, basically. Those products which became SVHC were most of the time, those additives, good accelerator for the amine epoxy polyaddition. So that's why it's generally the challenge to remove the SVHC is to get still the fast cure. On the graph on the left, we have plotted the reactivity in the y-axis and in the x-axis, the VOC content. The size of the bubble is proportional to the viscosity, and the absolute value is also mentioned below the product name. You can see that Aracool 3077-1 is VOC-free, SVHC-free, low viscosity, and still has a good reactivity. On the right graph, we represent more details about reactivity. You can see on the x-axis the thin film dust-free time at 5 degrees, and on the y-axis the full cure time at 23 degrees. The size of the bubble is proportional to the gel time at 10 degrees, and the absolute value is given below the name. In general, all those hardeners are pretty fast, but with this type of test at low temperature, we could find some clear discrimination. If Aradio 33641 is clearly the faster product of this range, it is pretty high in viscosity, and the pot life is really short. Aracool 3077 is actually a very good compromise of a decent pot life combined with a potential cure at 5 degrees and a low viscosity. Now let's focus on the sustainable hardener family, and let's say part 1. For curing component for low VOC and low temperature cure. So in the family of polyamidoamine, Aradio 115 is a reference for anti-corrosion. The problem of this product is a need of a high solvent usage because it's basically very high viscosity. As discussed before, when you try to reduce the amount of VOC, you need then a lower viscosity component. And you do not get much physical drying, so you really need to increase your reactivity. On the graph on the left, you can see 3 polyamidoamine hardener. In the y-axis, the reactivity is represented, and in the x-axis, the VOC content. The size of the bubble is proportional to the viscosity. You can see that Aradio 33225 is 0 VOC with a low viscosity, but you also see that the product will not react properly at room temperature, especially on a thin film. This product finds its use in high temperature application for manufacturing big pieces of equipment without having an exotherm. Aracool 1034 is, in the other hand, extremely reactive with a limited amount of solvent. It is used in low temperature cure anti-corrosion high solid application, even at 5 degrees. On the right graph, the product has been compared with a standard phenylcamine, and in the y-axis, left axis, you can see that on the thin film, the Aracool is 2 times faster for drying at 5 and 23 degrees, and in the y-right axis, we represented the pot life, and you can see that the pot life is twice longer for the Aracool 1034. This is really the key differentiator for this Aracool to cure extremely fast with still a good pot life, sorry. Unlike many other polyamidoamine on manic basis, Aracool 1034 does not contain residual-free small amine, nor it contains SVHC. The tox profile is then much better than fast product like that. So now we move to a second part of the sustainable hardener family with curing agents for compromise surface. compromised surfaces. In a view of improving adhesion on compromised surfaces for anti-corrosion coating, Curative did evolve by modifying the polyamidoamine technology and removing the free amine. So Arduino 450, Arduino 450-1S were developed in that view and show very good results in anti-corrosion, even on cold rolled steel, for example. Later, Arduino 3282-1 was developed, and as you can see on the left graph, it does not contain VOC, which is an improvement in the context of reducing VOC, obviously. The trade-off is that it is slower. Our Cool 1047 is actually based on a different technology and enable a really faster cure compared to others, keeping a really good flexibility and only 20% VOC. On the right graph, you can really see the reactivity difference, especially at 5 degrees for our Cool 1047. In this case, if the coating is dry to touch at 5 degrees in 3 hours, the pot life is unfortunately also very much reduced. Here, still same Hardener family for compromised surface. This slide you can see our salt spray accelerated test result on cold rolled steel with reference Arduino 115 on the right side. Our accelerated test is just a blend of resin and hardener without additives. So actually 500 hours is a very good value considering it's not really easy to adhere on this substrate cold rolled steel. The 3 modified polyamidoamine show much better results than reference, as you can see from the delamination around the scribe. And in general, Arduino 450-1S seems to give the best result with this test. It provides a fast cure and is SVHC free. Arduino 3282 is also VOC free, but it's much lower cure. And the Cool 1047, which is also give a very good result, maintain a very good flexibility, despite a very fast cure, is a really good accelerator for Arduino 3282-1. In the context of VOC reduction, another technology we focus now is the Waterborne Technology, and here we wanted to discuss the temperature boundaries for cure and optimization of corrosion resistance. So why Waterborne? Waterborne is interesting because it really helps to reduce the viscosity, and also you can combine it with some physical drying compared to the ice solid technology. Waterborne is definitely an interesting technology, yeah. But one of the pain points is that you cannot see the end of pot life. So when you take a waterborne system, you generate these organic droplets containing the resin and the hardener. They are dispersed in water. The reaction is taking place into each droplet, and with the advancement of the droplet in a pot, obviously. Nevertheless, if the droplet could become totally solid, the viscosity in the pot would not increase, or would increase, but not that much, and there is generally no visible end of pot life. If you would then do an application, the water will evaporate, the droplet will concentrate, and to get the film formation, you need those droplets to coalesce, to come together as one. If they are solid at drying temperature, they will not, and you won't have a good film. It will be matte. If the droplets are still liquid, then no problem. You will end up with a good glossy film. It means the drying temperature is above the minimum film forming temperature. For each system, resin and hardener combination, you can measure the non-visible end of pot life versus temperature. On the example on the left, we compare a slow hardener with 2 different resins, a solid dispersion and a resin emulsion. It's clear that at 7 degrees, with a very slow system, there is no way to use a solid resin, as there will be no coalescence. For the waterborne emulsion, the pot life would be around 3.5 hours. Of course, other problems could come at 7 degrees, as it would be so slow to dry. You could then get plenty of other reasons for surface defects. On the right side, you can see that with an Aradur of 3986 and different waterborne resin, you can really get good results in the 500-hour salt spray testing on cold rolled steel, especially if you compare with a solvent board system type 1 epoxy and an Aradur 115, which is a picture on the right side. So waterborne epoxy is really a good technology in the context of anti-corrosion coating, but you need really to take care of the non-visible end of pot life. It is why, and also why we wanted now to present a waterborne accelerator, a new waterborne accelerator called LME 11560, which is an accelerator which can cross-link and with plasticizer free. So if there is different waterborne hardeners with different reactivity, different flexibility, accelerating waterborne has always been pretty challenging at room or at low temperature. Generally, the accelerator will come as a third part, just added at the end, as it would not be soluble in a waterborne hardener, and it would not be possible to formulate in the epoxy part for obvious reasons. Also, adding a third part would destabilize the emulsion and would not help that much. This new component, LME 11560, is a reactive, water-soluble accelerator that you can formulate in any waterborne hardener. It provides or reveals a visible end of pot life. In reality, it accelerates so much that gelation in pot would occur before non-visible end of pot life. Then, an applicator will not be able to apply after the non-visible end of pot life. The use of large amount of this accelerator does not change the thermomechanical properties, as it maintains a very good flexibility, which is not so common for an accelerator. Usually, accelerator promote homopolymerization of epoxy, which means higher cross-linking density. On the graphs, you can see the effect at 10 and 26 degrees on the drying time by substituting Aradur 3986 with this new accelerator. We consider actually here that they have the same H+ equivalent weight, basically the same mix ratio. With 50/50 Aradur 3986 accelerator, you can divide per 2 the drying time at 10 degrees. We have also reported the visible gelation time, which is around 50 minutes at 10 degrees or 30 minutes at room temperature. On the waterborne topic, we wanted to discuss about these components, phenoxy. And phenoxy, what they are these long-chain polymer made from bisphenol A and epichlorohydrin. The structure is represented here, and you can see the aromatic backbone, which confer good hydrophobicity, and the hydroxy group on the side, which help for the adhesion. Those polymers are solid thermoplastic, which are here with the grade PKHW 34, 35, and 38 dispersed in water. It allows the addition into a system without use of solvent. That's the interest of the waterborne dispersion. In principle, those can be used as additive, about 5% max, for adhesion promotion and for increasing flexibility and reducing crack resistance without compromising hydrophobicity. In principle, the hydroxy functionality makes the material cross-linkable with molecules like isocyanate, anhydride, or other silane. Their key property improved in an epoxy coating would be clearly the anti-corrosion due to the structure of the material. Another booster we wanted to discuss here in the part of efficiency is an additive called DW1765, which is here to extend the overcoatability without impact on corrosion resistance. So the modifier DW1765 is an interesting additive. Why? Because by adding less than 3%, you can really improve the recoatability of a coating. Why? Because it's an epoxy-based product which protects basically the surface during the cure. When applications are done in cool, humid conditions, it is often difficult to avoid different phenomena like blushing, water spot, stickiness, or carbonation also. Those defaults are generating a weak link for the potential next coat. And sometimes this potential next coat can be applied months later. On the graph, you can see the reference system cured at 5, 10, and 23 degrees. And the water spot resistance is shown in the y-axis. The size of the bubble is proportional to the quality of the surface appearance, and the color tone to the recoatability performance. So the darker, the better. Generally, all parameters are improved at all temperature, as you can see, by adding 2 to 4% of the DW1765 in the resin. And another interesting behavior of this modifier is that it can also help for scratch resistance. Accelerator is also a booster, and here we wanted to present a special accelerator on 2950 for low temperature cure. So this accelerator is non-plasticizing and a non-plasticizing accelerator which has some interest as it would not leach out of any coating. So in many cases, there is always a need to accelerate a system, and to add accelerator in an hardener is quite common. So for instance, Radius 3282-1 we've seen before is a bit slow. Here it was chosen as a system to accelerate. Generally, the accelerator used in the industry is accelerator 960-1, which can have other name, and this product is good, but the quantity you can add is limited as it acts as a plasticizer. The result of acceleration is shown on the graph on the left. Clearly, it does accelerate at room temperature, but at 5 degrees, you need 20% to start seeing an effect. And 20% would be really too much, as you would damage the property of your coating, as it is also plasticizing the coating. On the right side, this is you can see the similar data, but this time with the accelerator 2950. The accelerator offers a chance to co-react with the epoxy network, allowing a better retention of the properties, even used at high level, which is interesting. An interesting fact is also the acceleration at 5 degrees is much more pronounced with 2950. With 10% accelerator 2950, you are already faster drying time at 5 degrees than with 20% accelerator 960-1. So now let's go to the durability part. And let's start with looking at the polymer design impact on corrosion resistance and the processability of different resin. And specifically, we will look at the flexibility and the hydrophobicity of those resin. So what we did is to plot a few epoxy to look at different parameters. On the left, we focus on flexibility, hydrophobicity, and viscosity of each epoxy. The product is those epoxy are fully cured with an IPDA-based hardener, and we decided to go on a fully cured material for the sake of comparison and a better discrimination, and so we can compare apple and apple. Down in the middle, you can see the standard BPA, bisphenol A epoxy resin Araldite GY250. You see the viscosity is 11,000 millipascal second, and x-axis, so we have the viscosity, in the y-axis, the elongation at break, and the size of the bubble is proportional to the water absorption after 3 days in boiling water. The absolute value in percentage is given below the product name. Interesting behavior is with Araldite PY4122-1, which gives 110% elongation at break with a relatively low water absorption, only slightly above the standard bisphenol A. Clearly, the drawback of this component is a higher viscosity, But to cope with viscosity, reactive diluent could be used with DYC, araldite DYC, or araldite DYO26. Araldite DYC offer a very low viscosity, but combined with a very good elongation at break and a relatively okay water absorption when you compare with the standard butanediol, diglycidiether, araldite DYO26. Those components can all be blended to achieve the optimization needed. On the right drives, we focus on adhesion and corrosion resistance. The size of the bubble is here proportional to the viscosity. Araldite GZ290X90 offers here a very good compromise between viscosity, adhesion, and anti-corrosion. This product provides really superior adhesion on compromised substrates. But next slide, we will first focus with on araldite PY4122-1 and its outstanding flexibility before we go for the GZ290. So we focus here on PY4122-1 and we look at the flexibilization in the coating and the barrier effect. So we have tested the product with a good adhesion and flexible reference, which is Aradur 450. This is a table on the left. On the right side of this table, you have then Aradur 450 cured with the standard bisphenol A epoxy resin, araldite DY250. Going left, we substitute this bisphenol A epoxy resin with araldite PY4122-1. If reference data already show good distanceability, impact strength, and adhesion, you can see that flexibility via bending test is improved. Also, the salt spray on cold roll steel is certainly improved. The reactivity is also decreased as there is less epoxy in the PY4122-1. On the right table, data this time are generated with a reference which is an Hardener Aradur 33641, and it's an Hardener which provides a high crosslink system. And we can see here that this reference is pretty brittle with a low distanceability, low impact strength, low flexibility, and bad adhesion. But the chemical resistance is then good. By exchanging GY250 with araldite PY4122, we see a decrease in reactivity, but a steady increase in distanceability, flexibility, impact strength, and partially on adhesion. The chemical resistance is also maintained almost at the same level than with GY250. It proves that with PY4122-1, it brings high flexibility, but it also maintains the chemical resistance of a standard bisphenol A epoxy and can, even in an extreme case, increase a bit the anti-corrosion property. Last but not least is the araldite GZ290X90 or N90 and its superior adhesion on compromised surface. So the GZ290 exists in two solvents at 90% solid, either in xylene for the X or in methoxypropanol with the M denomination. On the left graph, we have represented some properties of three resins cured with the same hardener. On the y-axis, you have the distanceability, and the x-axis, the flexibility of the coating. The size of the bubble is proportional to the adhesion strength. What we can see that the liquid bisphenol A epoxy resin is way less flexible than a solid bisphenol A epoxy resin, but actually the adhesion strength of the solid one is not strongly improved. On the other hand, araldite GZ290X90 allows a much better flexibility than a standard liquid epoxy resin combined with an improved adhesion. On the right side of the slide, the anti-corrosion performance of this product versus semi-solid epoxy resin or liquid epoxy resin is represented, and it gives a similar trend. Araldite GZ290 on cold rolled steel give much better salt spray result due to an improved adhesion behavior. And that's how I conclude my technical parts.
Oh, thanks a lot, Alex. Loads of details to digest for everyone, I'm sure. So just to finalize this presentation, I would just like to summarize a bit what you've heard. So as Alex explained, we optimized our portfolio to address multiple needs in the area of corrosion resistance and durability. So attributes like mechanical strength, adhesion, carbon footprint, speed of cure, and hydrophobicity we address through polymer structure and polymer design. And we at the same time, we keep product features like SVHC-free and VOC-free components in the offering. So to summarize, we can say that our multiple components allow the formulators to deliver sustainable VOC and SVHC-free formulations. And our components also allow you to fine-tune your coating towards curing speed, curing temperature, application performance, and also overcoatability by combining those multiple components with each other. So with that, we are at the end of our presentation. Let's have a look at your questions. Sarah, can you maybe assist us there?
Sure, Kerstin. And thank you very much, Kerstin and Alex, for all these valuable insights. So as you said, Kerstin, it's time to open up for questions and, of course, answers. Let me have a second to look at what we have got so far. I see here one that I can pick up immediately. I think this is for you, Alex. So the question is whether formulated using zinc cast anti-corrosion pigments will eliminate all these differences.
No. Sorry. Okay, I understand the question. I understand is basically by taking a zinc-rich formulation by adding either some booster or modifying the binder, the polyamidoamine, for instance, would change. If adding zinc would kill the property I described today, I would say simply no. I don't expect that. I think the improved adhesion is there and will remain there. Whatever filler you add, the only compromise is always in the viscosity. But this is nothing we can do more than giving our initial viscosity.
Thank you, Alex. So let's go for the next one. It's also for you, Alex. We'll keep you busy. From the long portfolio, what would be your recommended choice for a room temperature cure high solid system on different metallic substrates?
Well, I like on different metallic substrates, so I would take Aradur 3282-1 as a base hardener, as an hardener, and I will think this hardener is maybe a bit slow. So I will tune my reactivity by using either the accelerator 2950 to accelerate to the level I need, or if I really want to remain very, very, very flexible, I could use Aracool 1047 XW80. And for resin, I would take the basic resin is always let's say GY250, but GY250 is not the best for difficult substrate. So I could use a GZ290X90 to improve the adhesion, or I could flexibilize with 4122-1 with Araldite PY4122-1. And if I need to manage my viscosity, I would use an Araldite DYC because it's a diluent which provides a special hydrophobicity and confer a good flexibility also.
Right.
I hope it answers the question.
Thanks, Alex. Otherwise, yeah, the chat is open, so please feel free to to add any comments or additional questions. So let's go for the next one. It's about, Alex, also for you, formula proposal for 1000 salt spray resistance in CRS. Do you need more clarification on the question, maybe?
No.
Okay.
I mean, the formula, I guess I will answer only on the organic part, on the part where I can discuss. I will, for 1000 hours on cold rolled steel, I will immediately go with GZ290, X90 or M90, because really what I've seen on cold rolled steel, it is a resin which works really in a superior way. And for the Hardener, if we are talking about, I mean, no need to be very fast or anything like that. I think the best result I've seen so far were with the Radio 450-1S. But Radio 450-1S contains a certain level of benzyl alcohol, and if that would not be possible to achieve the ice solid, because here it's not mentioned if it's for ice solid, so if it's for 100%, then you have to go with something like 3282-1.
Thanks a lot, Alex. So here we have now one for which I can partially get an answer, but I will need still your support, Alex, on because there are many questions in one. And this is about the LME 11560, the waterborne accelerator, which is in development phase that you have presented earlier. So the questions are whether it is commercial, about the toxicology profile, regulatory compliance, and also about anti-corrosion tests. So no, the waterborne accelerator is still in the last stages of development, about to be scaled up. The plan is to go or to launch it commercially beginning of 2022, next year. Regarding the toxicology profile, I think, yeah, I mean, it is included in the toolbox that Alex was presenting at the beginning. So it's VOC-free and also SVHC-free. So all of the substances are actually, low toxicology substances in this component. Regarding regulatory compliance, the product is actually a reaction of two polymers, so meaning it's a polymer, and as such it's exempted from REACH registration, and it is also not fully worldwide registered, but most of the registered in most of the regions besides being exempted from REACH. So maybe, Alex, you can jump in with the anti-corrosion tests, which is the last question related to the waterborne.
So we do not have done yet the anti-corrosion tests, to be fully honest, but we have done adhesion tests and flexibility tests, which give a very good result. Really, we don't change anything in let's say, making worse for Ericsson type of testing. I would say this product is, as mentioned by Sarah, is really polymeric, but is accelerating out really a lot, actually. In anti-corrosion, this is going on. This is something we are looking at right now, because it's anti-corrosion is not necessarily short-term test. But I really do not have concern there. From what we've seen, and to use, the result looks very good, and up to now, even use the product pure basically as a sole hardener. The product remain flexible, which really, as I said, for an accelerator is pretty unique, and that's why That's why we don't expect problem. There was a question regarding storage stability with this product.
Yeah, it's another one, but it's the next one also linked to the same booster.
So I mean, there is no storage stability issue. I mean, of course, once you mix your resin and hardener, there's no storage anymore. You definitely need to react. But for the product by itself, the specificity of this waterborne accelerator is that it's water soluble. So when you mix it with an hardener, it's stable because most of the waterborne hardener, they are soluble in water. So you really have no issue at all, and you can really blend and have the right compatibility, and there is no issue here.
Thanks, Alex. So we still have time for more questions. The next one, Alex, also for you. Do you have any system which might survive 720 hours of salt spray test spread onto a steel substrate?
On steel, well, steel or cold rolled steel, if it's okay on cold rolled steel, it will be okay on any steel. So yes, as I kind of answered already this question. If on 100% solid, I will go with 3282-1. On something more ice solid, I will go for Radio 450-1S, and where I have a bit more reactivity. So after, it's a matter of reactivity and how fast you want your system to cure and how much pot life you can live with. So it's really depending on your use.
And the resin?
And the resin, of course, if it's cold rolled steel, as I said, GZ290X or M90. Maybe now the future is more with the M90 because the M is methoxypropanol, which is less concerning than xylene.
Thank you, Alex. Related to the xylene you were just mentioning, we have the next question. Regarding the problematic EHS profile. How do we generally replace it, and what are the consequences?
So there was more recently in the past few years a question about xylene. As you all know, xylene was a solvent of choice in coating. So xylene butanol or xylene isobutanol. But xylene, so there was an easy one, which was to replace it with orthoxylene. In Europe was done because some legislation in some country. Is it really sustainable? I'm not sure, but I think methoxypropanol, honestly, is the one of choice because it's not xylene. Maybe there is price issue or things like that, but in principle, we don't see so much tox concern, especially for a country like Asia. Methoxypropanol was a good choice. Asia is not a country, but in principle, the consequence, I mean, it's clearly the evaporation rate. I am honestly limited to tell you for the detail of application. Generally, when you replace xylene, you have to compromise a bit on the viscosity of our product. If I take an hardener, xylene is better than butanol.
Can you compensate with some reactive diluent?
Well, yes, you could compensate in the resin for sure, but in the hardener, it's a different story. You can compensate with a low viscosity hardener, but that could be some other problem. But in principle, it's difficult to comment on the drying and so on. I don't see much difference really, but you would, because you are more expert than me in this phase of drying.
Thank you, Alex. We still have a bit of time. To reduce viscosity in an epoxy part, what would be the diluent you would use, and why did you not recommend monofunctional epoxy?
Okay, fair question. So, it's 1, 2, 3. There is some cohesion. You want really to flexibilize a system. It's true. You want to keep hydrophobicity, and it's true that monofunctional epoxy like C12, in our case it's araldite DYE, C12 glycidilator is the best to reduce viscosity. No doubt about that. It's also a C12, so C12 mean C12 carbon, which means it's quite hydrophobic also. So I will not disregard it. It's just I cannot do a test with a monofunctional because I don't have cohesion. And the interest of having difunctional is that you still keep a certain degree of cross-linking density. And ideally, if you keep this degree of cross-linking density plus a certain level of flexibility and hydrophobicity, that seems to be the sweet spot. But I honestly don't say DYE is bad. Araldite DYE is very good. But in some case, you will find beneficial to use an araldite DYC.
Thank you, Alex.
As well.
Yeah.
Okay, let's go for the last one. We still have a few minutes. So from the whole presentation, whether we could highlight any particular performance on aluminum substrates.
Difficult question. I don't have data. I can only say I don't have data at all. We can't run. We generally want to do fast tests, to be honest. And it's very interesting area. It's I would honestly think that in the epoxy is a good candidate for aluminium. From my experience in the adhesive field, I would say that epoxy generally stick quite well to aluminium. There is a valid point to add some additive to improve adhesion. It's very visible with aluminium. Something actually I would like to run as a test, real test, but I'm fairly sure that it will work pretty well with a product like Hardener 450-1S with GZ290X90 would work pretty well on an aluminium compared to all the technology, not old, but let's say mature technology like Hardener 115, because a big problem of the mature technology is that it was a residual amount of amine or the lack of flexibility. Some case, and on aluminium, I think it would be positive. The product we presented.
Thanks a lot, Alex. We still have one question. I would like to, not going much behind the time, but I think we can still take it up. Recommendation for cleaning, Alex, of the waterborne epoxy dispersion, for example, pipeline solubility of the waterborne epoxy dispersion.
Water is good. No, it's true that one of the advantages of waterborne, it's not a joke, is that actually you can really clean with water. Maybe in general, for me, I would think something like isopropanol is very good to put with anything. Isopropanol is miscible with water and is miscible with a lot of organic things. So to clean, it seems a very good choice. That would be my answer.
Thank you, Alex. So let's keep it here for today. We hope we could raise your interest today. For any further follow-up questions, please get in contact with us, as I said at the beginning, either via our sales representative or also at our Hardener website under the contact / advanced materials section. And of course, if you would like to stay up to date on our news, please follow us on social media. We would like to thank you all again for your participation today. And before we conclude our webinar, please remember to take part in our survey. Thank you very much for your time, and we look forward to seeing you all at our next durability webinar session. Stay safe and wish you a very nice rest of the day. Bye now.